In numbers 91 and 93, what we basically do is we're adding another layer to our existing framework. So we've learned how to go from moles of one thing to moles of another thing using the mole ratio. So we've got that going for us. And we've learned how we can make that more complicated when we go from grams of one thing to grams of another thing. So that involves more steps, right? We've got to use molar masses and mole ratios. From there, we added another complication, limiting reactant. So that adds another step onto the beginning of our problem. We want to figure out what reactant is limiting, and then we can get to our nifty little diagram here and go from grams or moles of one thing to grams or moles of another. 91 and 93, we're adding something called percent yield to the end of our problem. So basically, this will just add another step for us, percent yield. If we can get to our regular diagram, we can calculate percent yields of things. An important thing to remember is that percent yield is equal to the actual yield, so what you actually get, over your theoretical yield, what you're supposed to get, times 100%. Usually you will be given the actual yield in a problem, so you're given the actual yield in both problems 91 and 93. The theoretical yield is something you solve for using your balanced chemical equation and your amount of limiting reactant and mole ratios and that kind of stuff. You can use those two numbers to figure out percent yield. 91, part A, you're given an equation of sulfide reacting with oxygen to form lead oxide and sulfur dioxide. And you want to figure out what the theoretical yield of lead oxide will be if 200 grams of lead sulfide is heated. So the first thing to do is we get to balance this equation. You can do this indicated here. So we want a 2 in front of the lead, a 3 in front of the oxygen, 2 in front of the lead oxide, and a 2 in front of the sulfur dioxide. Once we've got our equation balanced, we can go to work. Luckily for us, we don't need to calculate or figure out what the limiting reactant is in this problem, because we're only given the amount of one of our reactants. We can assume that oxygen, the other reactant, is in excess. So what we're going to do is we're going to start with grams of lead sulfide, and we're going to work our way around our diagram till we get to grams of lead oxide. We're going to start off by using the molar mass of lead sulfide to go from grams to moles. Once we have our moles of lead sulfide, we can go from moles of lead sulfide to moles of lead oxide using the mole ratio. Once we've got, that'll give us our moles of lead oxide, and once we've got that, we can go from moles of lead oxide to grams of lead oxide. In order to do that, we use the molar mass of lead oxide. From there, it's just a matter of arranging our conversion factors so we can cancel out what we want to cancel out and be left with the units we want to be left with. First thing we're going to do is divide by the molar mass of lead sulfide. If we do that, our grams of lead sulfide will cancel out. We're left with moles of lead sulfide. From here, we're going to use the mole ratio. According to our balanced chemical equation, that mole ratio is 2 to 2. We want moles of lead sulfide in the bottom, moles of lead oxide at the top. If we stopped here, would figure out how many moles of lead oxide would be produced from this chemical reaction. We want grams, so one more step. We want to go from moles to grams. In order to do that, you use the molar mass of lead oxide, and the units we're left with here, if we set it up correctly, are grams. So our theoretical yield, what we're supposed to get if we have 200 grams of lead sulfide, is 186.6 grams of lead oxide. Now that we've got our theoretical yield, the mass of lead oxide that's supposed to be produced, we can solve part B, which asks us, okay, if we actually get 170 grams from this reaction, what's our percent yield? So I have the formula for percent yield written down to the right. It's just a matter of plugging things in. Our actual yield is 170 grams. Our theoretical yield is what we saw for earlier, 186.6 grams. Plug it in, do the math, you end up with 91.10% yield. Question number 93 puts everything we learned in Chapter 11 together in one problem. We're given a balanced chemical equation and masses of our two reactants, SiO2 and HF, so silica dioxide and hydrofluoric acid. From here, we're asked a series of 4 questions. We want to figure out A, what the limiting reactant is, B, what's the mass of the excess reactant, so what's the mass that's left over, C, what's the theoretical yield of hexafluorosilicic acid, H2SiF6, so what are we supposed to get? And D, if we actually get 45.8 grams of this hexafluorosilicic acid, we want to know what the percent yield is. So we got to do this step by step. Part A, we want to figure out which reactant is limiting. Okay, I'm going to do this using the what if, how much method. I feel like this is a little bit more straightforward. So we've got our mass of SiO2. What we're going to ask is, what if all of this SiO2 reacted? How much hydrofluoric acid would we need? To do this, we're going to go around our diagram. So we're going to go from grams of SiO2 to moles of SiO2. We'll use our balanced chemical reaction to go from moles of SiO2 to moles of HF, and from there we can go from moles of HF to grams of HF. That'll tell us how much HF we'd need to use up all of that SiO2. So to go from grams of SiO2 to moles of SiO2, we're going to divide by molar mass. That'll allow us to cancel out our grams. Right now we have how many moles of silicon dioxide we start off with. We can go from moles of SiO2 to moles of HF using our balanced reaction. What our reaction says is that each mole of SiO2 will react with 6 moles of HF. We want to cancel out moles of SiO2 and we want moles of HF, so we want our moles of HF in the numerator and our moles of SiO2 in the denominator. If we stopped here, what this would tell us would be how many moles of hydrofluoric acid we need to react with our 40 grams of SiO2. We want to go one step further. We want to know how many grams of HF we need to react with all of our SiO2. So we just need to use our molar mass of HF to solve this. We want grams in the top and moles in the bottom because we want to cancel out our moles. So if we do all these conversions, we end up with 79.9 grams of HF. That's how much HF would need to use up all of our SiO2. We have 40.0 grams of HF. That's not enough. So we have less than what's required, which means that our HF is limiting. So there's our answer to our first problem. Hydrofluoric acid is our limiting reactant. Part B asks us how much of our excess reactant is left over. Okay, we've done this before. What we need to do is we need to figure out how much of our excess reactant reacted. And then if we subtract that from our total, how much of that reactant we started out with, we can figure out how much is left over. So in order to determine how much of our SiO2 actually reacted here, we start with our mass of HF. Right? That's our limiting reactant. We can go from grams of HF to moles of HF, moles of HF to moles of SiO2, and then from moles of SiO2 to grams of SiO2. 3 steps. We're going to go around that whole diagram again. So we start off, we use the molar mass of HF to cancel out our grams of HF and get moles of HF. From there, our balanced chemical equation tells us that 6 moles of HF will react with 1 mole of SiO2. So there's our mole ratio there. We want to cancel out moles of HF, so we want 6 moles of HF in the denominator. And in order to determine how many grams of SiO2 reacted, we're going to multiply our moles of SiO2 by the molar mass of SiO2, 60.084 grams. To set it up correctly, our moles should cancel out, and we'll be left with 20.0 grams of SiO2 that reacted. We started with 40 grams of the stuff. So the mass that's left over is equal to what we started with minus the amount that reacted. 40 grams minus 20 grams. We have 20 grams of SiO2 left over. In part C, we want to know what our theoretical yield of H2SiF6 is. So this is basically like a problem from earlier in the chapter now. So we're going to go from grams of our grams of our limiting reactant to grams of our product. Right? We're going to go all the way around this diagram here. So it's kind of set up similar to the first step in part B. We're going to go from grams of HF to moles of HF, from moles of HF to moles of H2SiF6, and from there we'll go to grams of H2SiF6. This is going to involve us first using the molar mass of HF to cancel out grams of HF. From there we can use the mole ratio given to us by our balanced chemical equation. It tells us that for each 6 moles of HF that are consumed, 1 mole of H2SiF6 will be produced. We want our H2SiF6 in the numerator, and we want to cancel out our moles of HF, so we want them in the denominator. Last step, we want to go from moles to grams using the molar mass of H2SiF6. We want grams in the numerator, we want moles in the denominator. If we set up our conversion factors correctly, this will tell us that 48.0 grams of H2SiF6 should be produced from our 40 grams of HF. That's our theoretical yield. All right, in part D, we're asked, what's the percent yield if 45.8 grams of H2SiF6 are actually produced? Okay, let's go over that formula again. Percent yield is equal to actual yield over theoretical yield times 100%. We calculated the theoretical yield in part C. So that's going to go in our denominator. We're told what the actual yield is. That goes in our numerator. From there, we just plug stuff in and do the math. If you set up your equation correctly, you should end up with 95.4% yield.